Great. Well, welcome everyone to the conference. I'm really pleased to be able to share something about my research and my journey into chemistry with all of you. And as you can see, I'm going to talk about solid state chemistry, what, how, and why. But I'm going to begin by just saying a bit about myself. So I grew up in South Cambridgeshire and went to a state secondary school and sixth form college there. And as I left school, I wasn't really sure what I wanted to do, sort of career-wise. And so I applied for the Year in Industry scheme run by the Engineering Development Trust, which will place school leavers with scientific A-levels into a paid internship for a year. And I did that staying at home, just commuting by half an hour across town at a company called Scalene, where I didn't do a whole lot of sort of chemistry specific stuff. I was doing a lot of spreadsheets, to be honest, and also sort of fiddling with microfluidic pumps and things. We were setting up a DNA processing system, and it was all very exciting because that introduced me to the idea of doing science in a way beyond what we'd done at school. So I had a really good time there, and during that year, I worked out that I wanted to study chemistry at university. I wanted a bit of lab work alongside just the study, so that sort of turned me away from doing maths, which was my other option. And I came to Oxford to do an M.Chem. So that stands for a Master of Chemistry. In Oxford, it's a 4-year course, and it's a little bit different from many other chemistry courses across the UK. In many other places, you can do a Bachelor of Science, a BSc, taking 3 years, and then you may be able to add on another year to make it into a master's course, which could be abroad, it could be in industry, or it could be in that same university city. In Oxford, you have to stay for the 4th year, so you have to graduate with an M.Chem, and the 4th year is entirely a research project. So having finished with exams after 2nd and 3rd year, I was then in a research group for my whole 4th year, sort of working a 9-to-5 job, doing experiments, designing my projects and working out some interesting things about chemistry. And I enjoyed that so much that I applied to do a PhD. Essentially, a PhD in the UK is 3 to 4 years of full-time research, and at the end you have to write a thesis about 60,000 words, which says everything that you've done and which scientific questions you've answered. The PhDs will normally be you will normally be able to apply for funded PhDs where the government gives you a stipend, or the university can give you a stipend to live on, so a sort of salary to live on while you're doing your studies. And so I was given one of these scholarships to spend 3.5 years in Cambridge doing my PhD, and I'll talk a bit about the research that I did there later on. And obviously there was COVID and all sorts of things happened in the middle of that. But in 2022, I came back to Oxford and started my postdoc. So I'd come to the end of the PhD and wanted to keep on doing research. And a postdoc is a normally 1 to 2 to 3 year short-term fixed-term contract to do some more research. I don't have to write a thesis at the end, which is quite nice. And I'm just getting to explore a new area of chemistry. So that's my sort of career so far. Whenever I do these talks, I always like to mention sort of other life. I can click. So in 2021, I actually took 6 months out of the PhD studies to have a baby. So that was stressful, but nice. I realise it's a long way away for many of the listeners, but I just like to show that a sort of academic career is not necessarily incompatible with having a family. I'm rather early on in my academic career. I don't know if I'll end up as a professor or a lecturer, but even sort of going through PhD and postdoc, wherever I end up, this sort of career has so far been compatible with having a family, which is very nice. I just like to tell people that, whatever the audience level. Okay, so today my talk is going to be what is solid state chemistry, because I'm aware that it's not a topic that's covered in a huge amount in the school syllabus. Then I'm going to talk a bit about what we do, what I do day to day in the lab. So how do we make these compounds? How do we measure them and investigate them? Then I'll give some examples from my past and current research projects to try and illustrate why it's important, why do we care, and where's the field going in the future. So I want to start by talking about interactions. You're probably familiar with 3 different types of interactions between atoms: covalent, metallic, and ionic. And actually all 3 of those can occur within solid state compounds. But when most people talk about solid state chemistry, they're talking about ionic interactions in a giant ionic lattice. So in this case, we've got sodium, which has lost an electron to form a sodium plus ion, and chlorine, which has gained an electron to form a chlorine minus ion, chloride ion. And because they've got opposite charges, they'll attract each other. Now what we have is not a single molecule of Na plus and Cl minus, but instead we have this giant ionic lattice, ionic network, made up of many, many millions of atoms. So remember, because they're so small, that even one single grain of salt contains far more atoms than are shown in this diagram. And we can also, of course, get giant structures with covalent bonds, such as on the left, carbon in its diamond form has got this the similar kind of 3D huge structure. So obviously, if you look at this NaCl, we've got to think of a way of describing this structure without sort of counting out every single atom. We can't describe it in the same way as you might say a molecule of carbon dioxide. We can't draw the whole thing every time we want to express what it looks like. So there's got to be a way to describe this structure. And what we do is we reduce it down to something called the unit cell, which is the smallest repeating unit of that giant 3D structure. So it's kind of like a box that contains some atoms, and you can imagine stacking up those boxes in all 3 directions, all next to each other, to form the giant structure. And if I wanted to describe this unit cell to somebody else and say, you know, this is the structure of NaCl, then I'd want to talk about the size of that box and its shape, so the lengths of its different sides. It might not be a cube, for example. The lengths of its sides, the angles of the corners, and the contents, so what the atoms are and where they go. So as an example, again for this, I would say it's a cubic box, and it's got sodium ions at each corner and in the middle of every face, and it's got chloride ions at the middle of every edge and right in the middle of the box. We can go a step further and work out how many atoms or sort of parts of atoms are within that whole box as well. So if you look at the corner sodium plus ions, because those corner ions are going to be shared between 8 adjacent unit cells, sort of it's there in that one, and then it's on the, they'll have 3 more in the same layer and 4 more cubes above it, then that atom is only contributing 1/8 to this unit cell. So we get 8 lots of 1/8 at the corners, making 1, and we get 6 lots of 1/2 in the faces, because each sodium plus ion that's in a face is shared between 2 adjacent unit cells in the bigger structure. So 6 times 1/2, which is 3, so we end up with 4 Na plus ions within the unit cell. And we do the same for the chloride and find that there are 4 of those. So that allows us to say the empirical formula is NaCl, which we knew already. So that's just an extra added bit of information that we'll use to describe this structure to somebody else. An alternative way, or an additional way of describing the structure is in terms of symmetry. So we can look at that unit cell and say, okay, where are the symmetry elements in this? Are there any mirror planes, for example? And yes, there are in fact mirror planes that cut the cube in half, sort of down the middle of each face. We've also got some 4-fold rotation axes, so like down the bottom of the unit cell and sort of into the page, as it were. And we've also got 3-fold rotation axes, which go from across the body diagonals of the cube. where you rotate it by 120 degrees and it looks the same. So those are symmetry elements that we can use. And another way to describe the structure is in terms of geometry. So look up at the chloride ion that's sitting in the very center of that top unit cell. Its nearest neighbor ions have all got to be positive, because that's the only way that the structure holds together. We've got to have positive and negative next to each other. And it's got 6 nearest neighbors. It's got 2 sodiums above and below, and 2 sort of left and right, and 2 front and back. And they're arranged in an octahedron around that central chloride. So we might say in that sodium chloride structure, we've got every chloride ion is octahedrally coordinated to 6 neighboring sodium ions. And you can say the same about the sodiums, actually. They've got 6 chlorides around them. So then in the examples at the bottom, we quite often describe structures a bit like this one as corner-sharing octahedra, and on the right, corner-sharing tetrahedra. With all that said, there is a sort of mathematical way of describing all of these structures that doesn't rely on quite so many words. It's a branch of science called crystallography, which is really sort of very intertwined with solid-state chemistry, but other chemists do use that science as well. And it's slightly too mathematically complex to do in a lecture like this, but it's a really interesting branch of science. There are 230 different space groups, which are sort of symmetry labels that we can give to different structures. So really, it can be very complex, or it can be, even though it looks simple, like NaCl, that's, there are 229 other different symmetry descriptions that we could use for other solid state crystals. So now I want to talk about how we determine those crystal structures. Obviously, these atoms are tiny. All we get is a little crystal, or a little spoonful of powder. So here is a diagram which shows the way that we determine these structures. We use something called Bragg's law, shown on the right. And how this works practically is we shine a beam of radiation, typically X-rays, at the crystal, and we measure how those rays of light get bounced back off the layers of atoms. It's called diffraction, which you may have seen in physics classes. So here what I've done is I've rotated the NaCl structure so that you can see layers of Na plus and Cl minus ions. And here these rays are bouncing back off the layers of Na plus ions. They're being diffracted by an angle called theta. And then, knowing the wavelength of the radiation, we can work out that distance d in between the planes, the layers of similar ions in the structure. So what we actually get, because it's not just a single crystal in our sample, we'll probably have lots and lots of crystals lying at different orientations to the incoming beam. What we get is a pattern where we get peaks at particular angles. And again, if you look at the Bragg's law, you'll see that as we increase in the angle, that means a decrease in the d spacing. So the atom layers are getting closer together. And what we can do is, it's possible to take this powder diffraction pattern that comes off the measuring instrument that we use and work out the structure just from scratch. That's a lot more difficult than it sounds, and it sort of gets infinitely more difficult the more atoms you have in your structure and the more complex the symmetry. So typically what we would do is look for materials that have a similar kind of structure. Quite often, certainly in the work that I do, I'm aiming to make something and I know that it's very similar to this other compound. I've just changed one atom, but it should be a similar kind of structure. So what I do is I take my model structure and calculate with the computer what the pattern would be expected to look like for that model. So that's on the right, that's my red line, my calculated model. And then we plot that next to the blue line, which is the observed data. And you can see that they're kind of quite similar, but they're not exactly the same. There's a difference line at the bottom, which is not exactly flat. right? It would be completely flat at 0 if the model was perfectly correct. So what we do is something called a refinement, because we're going to take that model structure and refine it or improve it by gradually moving atoms a tiny bit, or maybe add another atom here and see if the model gets better. And if it does, then you accept the move. And if the model doesn't improve, then we put the atom back where it was. And you sort of tweak it and move the atoms around until you've got a good fit between the model and the data. So it's almost like working backwards, because where do we get that data from? Well, we get it from the samples that we've made. And when people talk about solid state synthesis, what this normally means is you'll also hear the term ceramic synthesis. What this normally means is samples are made from reagents that are also in the solid state. So there's none of this mixing and stirring liquids and heating them up. It's you'll get powdered reagents. We grind them very well together and heat them up. And the reaction happens in the solid state, so that the sample never melts at all. That's very important. And what happens is that you've got different grains of your reagents, and the reaction happens, because it's solid, it's not all melting together. The reaction happens by single atoms diffusing across the boundary between those grains. So it's very slow, which is why we need quite high temperatures to make this happen. And this is also why we want to grind up our samples, our starting materials, into a very fine powder at the beginning, in order to get their surface area as large as possible. We also then press that mixed powder into a pellet. So putting the pressure on it kind of pushes all the grains together and makes them react a bit better. And then a typical thing is we put the sample in a furnace, heat it up slowly, leave it there for a bit, and then cool it down again to take it out of the furnace. And you can see that all of these steps will have different things that we can vary in order to make the reaction better. So the heating rates, the cooling rates, how long it stays at the highest temperature, and what that temperature is. But the key thing is that because it's high temperature synthesis, and because of the way the atomic diffusion rules how the sample is made, we're always going to form the most stable possible product. And the problem is that in solid state is that if you form a mixture of products, what it is actually you've got tiny grains of all those, say, products A, B, and C, and they're all mixed together, and it's not normally very easy to separate them. So this is why a large part of solid state chemistry work is tweaking the synthesis, trying different heating rates and different temperatures and different times until you find the best set of parameters, the best temperature and whatever, to get the best sample out. Because we can't separate out any side products in the same way as you might filter out a solid from a liquid. We just can't do that with a solid that's a mixture of different parts. So sometimes we can do these reactions under flowing gases, because we might want to keep the sample away from air, for example. So we can do it under flowing nitrogen, which won't react. However, some samples really react with air, and you've got to keep them away from. You can't even take them out of the furnace, because as soon as you take away that gas flow, then they'll start reacting. So what we normally do is seal them inside a container, but that container can't have any other gas inside, even something inert like nitrogen, because if you heat it up, it'll explode. So we have to seal it under vacuum, and we do that in glass tubes. And this is probably the most fun part of my job, is using the blowtorch to seal samples inside these glass tubes. So that's me doing my fourth year project. And then at the end, once that glass tube has been heated in the furnace and cooled down with the sample inside, we've then got to take it inside a glove box. That's what's shown on the top right. It's there's a sort of airlock, and then you take it in, and it's filled with an inert gas, in this case argon. Take it inside and then break it open to get the sample out. Then we've got some other setups in our lab as well for air-sensitive samples. At the bottom, it's a sort of vacuum rig where it allows us to transfer reagents between bottles and add other reactions and so on without exposing the system to air. So with that in mind, why are we interested? Why would you want to study solid state chemistry? Well, I'm going to assume that most of you are watching on a device that uses lithium-ion batteries, obviously hugely important to modern life, and that completely relies on solid state chemistry. I'll mention it a bit later. But there are all sorts of other things as well that that rely on solid state chemists to work out what material is best for that application. I'll mention some more details on a few of these in a bit. But to be honest, I got into solid state chemistry because I was interested in structures and geometries. We had a really interesting lecture course where I just sort of fell in love with all the patterns and the mathematics of it. And I think that's fair enough, to be honest. Lots of people hear about my research and say, so what's the point? And I go, well, it's interesting. So I hope I'll convince you of that in a minute. So I'm now going to give a few examples from this list and talk about research from my previous work, a little bit about my current work, and some of work from some of my colleagues. Okay, so going to start with magnetism. Most of you are probably familiar with the idea of a magnet, right? It sticks to things. But you might not have thought about the atomic, what's happening with the atoms and electrons within that magnet, what's causing it to be magnetic. So any atom that's got an unpaired electron will have a spin, so the electrons will tend to pair up, and if you've got an odd one, then it's got to be on its own, and that causes the ion or atom to have a spin, which doesn't mean that it's actually spinning, it's just a sort of weird physics property. And we model it as a little vector, a little atom, a little arrow on each atom. And these arrows, these spins, can line up and arrange themselves in different ways. So at high temperatures, all of those spins will be kind of moving around, fluctuating all the time. There won't be in any particular order. And that's shown on the right, that's a paramagnet. This is just sort of like a snapshot at one point, but those spins will just be moving around freely. As we cool down, we'll get less and less thermal energy. The spins move less and less, and they'll probably settle into one of these two arrangements. So on the left is a ferromagnet where all the spins like to be aligned parallel to all of their neighbours. And that's what we get in what you think of as a magnet. Things like iron and nickel, where they've got a permanent magnetism, all sort of pointing in one direction. Another option is an antiferromagnet, where each spin likes to point in the opposite way to its neighbours. So we get this kind of chessboard arrangement. And the choice of ferro or antiferromagnetic will depend on the exact atoms that are involved. Here is an example from my PhD work, where it's slightly more complicated because it's in 3D rather than 2D, but it's an antiferromagnet. So if you look at the chemical formula, we have oxygen, which forms O2- ions, terbium forms +3, and tantalum forms +5. And of those ions, only terbium has got unpaired electrons. So that's the blue ones. So that's the only magnetic ion. And if we cool this down low enough, then that forms an antiferromagnetically ordered system. So if you take, for example, look at one of the blue downspins, it's got 4 nearest neighbour spins, and they've all got to point up. So any spin has got to be pointing in the opposite direction from all of its nearest neighbours. Another aspect of my previous research was on the magnetocaloric effect, which uses a method of putting a sample in and out of a large magnetic field to have an effect on the temperature. So caloric is the temperature bit. Essentially, we use the large field to make all the spins line up, and then but if you do that in such a way that you could control where the heat transfer goes. And this is being researched as an alternative to normal fridges. So a normal fridge in your house uses pressure as the way of changing the temperature. It compresses gases. But some of these are not very good for the environment, so people are looking into alternatives to that. Also, at very low temperatures, researchers use helium particularly to cool down large magnets in MRI scanners. But unfortunately, helium is slowly running out. It's getting very expensive because it just gets lost into the atmosphere because it's so light that we can't get it back. So researchers are looking into different magnetocaloric materials in order to reduce our use of helium. And these magnetocaloric materials have got to have magnetic ions in so that they'll respond to the magnetic field in this way. So here's my example, which is a family of calcium lanthanide borates, where I studied how strong is that magnetocaloric effect, how strongly does it respond to a magnetic field at different temperatures. And I found that these materials are not amazing, but they're sort of similar to the existing sort of state-of-the-art materials that are being investigated for this purpose. And actually my purple compound was even slightly better at low fields. Magnetic refrigeration is not really a commercial technology yet. So there are other problems with building these devices. Not least they need to use large magnets, which can be expensive, but it's really an emerging area of research. Closely linked to magnetism is superconductivity, which means a system that conducts electricity without any resistance. Therefore, it doesn't lose any energy as heat, whereas if you think about copper wires and things, they'll get hot after they've been used for a while. And that would, if we could find a superconductor at room temperature, that would completely revolutionize electronics and everything that we use that involved electronics and wires through the national grid and everything. So that would, I'm sure that would win a Nobel Prize if it was discovered. Unfortunately, most superconductors that have been discovered so far have this critical temperature much lower than room temperature. So here's an example that one of my colleagues has worked on. This is a material called YBCO. It's got yttrium, barium, copper, and oxygen. And that's a superconductor because of the square layers, the square planes of copper and oxygen. But unfortunately, it only superconducts below about -200 Celsius. We can get to that temperature with liquid nitrogen, which produced the most fun experiment of my undergrad, because you can, a superconductor, as well as conducting electricity very well, also repels magnets. So in the picture, we've got a large black pellet of a superconductor, and it's been cooled down low enough that it will levitate a small magnet on top. So we did that when I was a second year, and I just thought it was really cool. Okay, on to battery technology. Perhaps maybe you're more familiar with this kind of idea. And this relies very, very heavily on solid-state chemistry research. A lot of research at the moment is going into looking at different materials for the cathode, the positive electrode on the left, and also as solid alternatives to the liquid electrolytes, because normally the material used in current lithium-ion batteries is liquid, can be very toxic. If it leaks, it can cause fires. So researchers are looking into solids as an alternative, but they've got to be solids that can allow lithium ions to pass through that material. So what happens here is that electrons pass around the outside circuit up the top, and within the battery, through the electrolyte, we get lithium plus ions moving between the cathode and the anode. So if you look at the cathode, which is on the left, we've got the purple layers are cobalt and oxygen, and the lithium plus are the blue spheres in between. As we charge the battery, those ions get taken out from in between the layers, and they move through the electrolyte, and they go in between the layers on the right-hand side in the graphite electrode, the anode. And this is called intercalation, which is where you're putting something in between the layers. And what we'd see experimentally is that you can see that we measure the distance between those layers, and that will increase as lithium ions go in between. And then as we take them out again, or as we take them out of the other side, the layers get closer together. That's de-intercalation, removing the ions from the layers, and the layers go together again. And the battery works because this cycle can happen many, many hundreds of times. Most current research, as well as sort of new solid electrolytes, is looking at optimizing materials so that they can cycle for more cycles without being degraded and running out. So you probably noticed that your phone battery sort of starts to die after 2-3 years, and depending on how many times it's been charged. So some of my colleagues are working on improving cyclability of different battery materials. Okay, and then this is just a little bit more intercalation. This is what I've been working on for the last year in Oxford. And I'm looking at these layered materials that contain 4 different elements, 2 positive, 2 cations, and 2 anions. And I've shown that, so here's the unit cell of my material, this is the repeating unit. And I've shown that if we react this with water, the water really likes to react with the alkali metal ions, the group 1 elements. And that causes de-intercalation. It reacts with the rubidium and pulls it all out of the structure, but it does it in such a way that the rest of the structure stays the same. So the layers that contain Te, Ti, and O remain the same as we go into that middle structure. All we've done is pull out the rubidium ions. So it's a little bit like what I showed on the previous slide with the batteries. I've then found that going from the middle compound, I can try to put the rubidium back in again, using a slightly more complicated reaction with featuring liquid ammonia below room temperature. And at the moment, we're still trying to work out if just the rubidium goes back in, or if some ammonia molecules also enter the system and sort of sit in between the layers in those spaces as well. But I think this is really interesting because even though it's not an element that can be used in batteries, and so I haven't yet made it work with lithium, it's really interesting because it seems like it might be an almost reversible system. We can take out these ions and then we can put them back in a different way, and we should hopefully be able to continue that cycle going back and forth. So my work at the moment is trying to expand this to other elements, including lithium, just really to see where this chemistry can go. Okay, so I'm going to finish now, and hopefully there's plenty of time for any questions about the chemistry, my career, university options, anything you like really that's vaguely related. In conclusion, I want to say that solid state chemistry, I hope I've shown you, is important in very many branches of technology, perhaps ones that you haven't thought about before. You'll like solid state if you like looking at patterns, symmetry, not too much maths, but a little bit. But I think it's the fun parts of maths, the geometry, diagrams and patterns. And the experiments are really fun. So glass blowing, I think, is the best bit of my job. There's also a lot of liquid nitrogen, dry ice, large magnets. We've got a machine called a squid, which stands for something weird, but it's basically a massive magnet. So I really recommend solid state chemistry, and I hope that as you go forward in your school careers, you'll think about that as an alternative to the chemistry that you typically do in school. Okay, thank you. That's all from me, and I'm open to questions.